Hello, good morning. This is 28th of February 2025, and I'm continuing my note taking series where I talk, type, and write and do. So, the next lecture is on vector fields, continuing the discussion on vector fields. We'll discuss vector fields as derivations, and we'll try to push forward the vector fields onto other manifold through smooth map, but turns out it won't make sense unless it is a diffeomorphism or satisfies some special condition, F relatedness, and we'll discuss such F relatedness of vector fields, the possibility of such of satisfying such condition in quotient manifolds with a group action. When you consider a gene variant vector field on these quotient manifolds, then then you get a related vector field, Q related quotient map, Q related vector field, in fact. So that's what this lecture is about. So maybe kind of small one, yeah. But first we'll start with a local form of this vector fields. So let's start. Recording. Cool. Yep, recording. So if let's consider charts on the manifold. If u, phi is a chart of M, phi equals to x1 xn, then the local frame. Okay, the local frame on Tm is basically the frame of tangent space at each point, right? At each point you can sort of define del by del xi at each point P, then that will be the local frame, basis of the tangent space at every point, basis of the fiber at each point. So then x1 dot xn is a local frame for Tm on U. Right, so we can summarize it in following. Tu is okay. Tu is locally trivial via the following chart, a series of charts, in fact. So first, through a chart phi tilde, one goes to phi of u cross Rn, and then from there one can use the phi inverse to go to the local realization. Such that see then you have the local realization. expression with phi of p comma yep. Okay. What? Oh. Mm-hmm. Okay. Mm-hmm. 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 Right. So that's good to put in, keep in mind. Now we have a proposition. Now we have a proposition that if X is a vector field of M, then locally it equals to some AI P equals to I, where AI in C infinity U. So yeah, locally it's written in the local frame simply, right? X of P, X of P equals to summation A square I of P, and yeah. Cool. Yeah. Basically, vector fields, vector fields provide a smooth way to move between tangent spaces of points in the manifold. Yeah. Yep. the equation 14 here speaks basically about the local trivialization. Say, yeah. Um. Mm-hmm. Yeah. 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 Recall that, like, no, like local trivialization. The form of local trivialization can be written in terms of local frames, right? So that's what we are doing here. The phi inverse of phi tilde of p comma ci, p comma c1 so on up to cn, is basically p comma c1 so on up to p comma ci del by del xi in terms of the local frame del xi, right? This can be again basically seen through the diffeomorphism itself, right? The local realization itself. The basis in Rn uh, can be basically lifted to, so yeah, of course, and many points and at many times we just ditch del by del xi and just write ci. That also works, but yeah, that also works. But especially if you are in Rn itself, then yeah, it's as a regular manifold and all that. But yeah, I think, oh yeah, one needs to write this properly. One needs to have a good exercise with this thing. So that's what we are going to do soon. So let's get to the examples. First example is consider our good old S1, where consider where x of x comma y equals to minus y comma x, and the chart and the chart u plus comma 5 plus, right? We want to write x on this chart, right, on this chart in the form of write the local expression the above proposition. La, 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 la. We want to write the local expression for x minus using the above proposition. So okay, so let's look at it, right? What is u plus? Equal charge on S1. Yeah. Okay, U plus U minus. Okay, by U plus we basically mean that phi plus will be equals to x by 1 minus y, I suppose, or y by 1 minus x, something like that, right? U plus, you use stereographic projection, and x comma y. This is t, right? So basically, yeah. So if this is y, 1 minus y by 1 equals to x by t. So t equals to x by 1 minus y. That is cool. And by u plus we mean that y is not equals to 1. Yep. So our chart of local expression is t equals to x by 1 minus y. Basically x comma y goes to x by 1 minus y. That is alright if we use theoretical projection. Now okay. So we have the vector field x comma y equals to minus y comma x. By minus y comma x, what we mean is minus y. I mean, it's an R2 to R2, right? You are looking S1 as a embedding in R2 as a regular submanifold in R2, and then the tangent space is actually a subspace, and then subspace of R2. So you are writing as an element of R2, right? Okay, but now if you want to write it in the above form, which is actually I equals to 1 to n, precisely means that it's single, right? You have only one sort of chart in this. So if del by del t was a basis element as a frame on R, then this is a bit confusing indeed. This is confusing. Yeah, but it's important that we realize this problem. So Yeah, so what we can write is minus del by del y plus x del by del x plus x del by del y, right, which is in R2 sort of, or in TPR2, tx comma y u was a subset of Rn, right, as a subspace of Rn, right. But yeah, but what we want to write here is to convert this into a single basis element as a something by del t, which is del theta, let's say, and this we want to identify this factor and also this factor. um, yeah, yeah, yeah. It's not exactly it's a subspace representation of this, right? Now you want to write this as some basis element, and how do you do it exactly? Right, there is some lapse in understanding that will definitely get cleared after once I do this problem. So okay. On S1 you are giving me a vector field in this notation, minus x comma y. Basically you are giving me a function from R2 to R2, because it is a submanifold, because it's a regular submanifold of TS TR. TS1 is a regular submanifold of TR1, which is basically similar to R1 cross R, basically R2. So in that way we are just managing things out. Okay, now we want to write, okay, cool. So basically these two should give you the same functions when you act on same values when you act on the functions from S1, from U plus to R, right? That's the best way to look at things, right? So yeah, so what is the claim? Del by del minus y del by del x plus x of del by del y times f is from U plus to R, f of p, let's say, should be equals to some a function which we want to evaluate, a of p by del t of f. Well, I mean, I think that is fine. Well, at p, a of p del by del t at p. Del by del theta is precisely the f star inverse, f inverse star of del by del t of f of p. So which is basically del by del t of phi inverse f of p is equals to this. Right. I think we are going somewhere. So minus phi del by del x del f by del xp plus x del by del bar y of f at p. We'll make it precise what this means. This means that del by del x of f of phi inverse of phi inverse of phi of p. Yeah, because that's exactly the lift, right? Is equals to a of p del by del t by dt of f of phi inverse of phi of p. Now, yeah. So from f is from u plus to r, yeah. It takes x comma y to some f of x comma y, and phi inverse is basically some t to, what does it, x by 1 minus y. That's what we wanted. T is equal to this, x square plus y square equals to 1, y x square plus, sorry, y square plus x is 1 minus t 1 minus y whole square t square equals to 1, y square plus of up to y 1 minus y is 1 minus y whole square t square equals to 1 minus y into 1 plus y. So t square equals to 1 plus y by 1 minus y. T square plus 1 by t square minus 1 equals to 2 by 2y. Y is equals to t square minus 1 by t square plus 1. T square plus 1 minus t square plus 1 by t square plus 1, which is 2 by 1 plus t square into t, 2t by 1 plus t square. Are you sure that this is correct? Something shady or a bit? whole square 1 plus y by 1 plus y. Add them, subtract them. So 2t by 1 plus t square, comma, so next so so again conclusion is not conclusion but the psi of p plus x del by del y f of phi inverse of phi of p is equals to a of p by d by dt of f of phi inverse of phi of p. This equals to a of p del f del d by del x f of phi inverse is from r to r. Yep. What the fuck, man? Well, yeah, it's basically r to r2 to r. Yeah. Oh my god. F of phi inverse. Great, man. So what I'm saying is you can write it as del f by del x times del phi inverse of shit by del t. plus del f by del y of times that is perfect. Yeah. Yeah. The fuck? Yeah, x squared plus y squared equals to. Makes sense, right? Okay, 1 plus t square of 2t minus t square minus 1 of 2t. Something's wrong, something's wrong, something's wrong. Something's definitely wrong. There has to be a explanation for this. Let's just see all of the problems again. Stereographic. So, yeah, for yeah, that's exactly what we got. But why aren't things matching up, huh? Oh, that is actually interesting. I mean, it really makes sense because minus y by x should be the ratio of these two coefficients, and in fact, it is exactly that. And yeah, I mean, Hoo, hoo, hoo. Hoo, hoo, hoo. This is non-trivial. This is non-trivial. How is this happening, man? Phi 1 inverse of t. T is basically okay. Yeah, I mean it's exactly that. 2t by 1 plus t square, comma t square minus 1 by 1 plus t square. Wrong, but there is some calculation mistake here. See, at t equals to 0, this is clearly phi inverse of t is 0 comma minus 1, which is exactly this point in the south pole. So I don't see any wrong mistake in this. But what must happen is d phi inverse of t by dt. If the first component, if you derivate, t square, it has to be different than the second component different. It's t square of I think it's 2t, not 2t square. Oh, oops. Yeah. It's 2t. I hope we got 2t, right? Yeah, it is 2t. Oh my god. Okay, that is the mistake. I think now things should fall. And so 2 minus 2t of 2t by 1 plus t square, which is 2 plus 2t square minus 4t square by 1 plus t square, 2 times 1 minus t square by 1 plus t square, and d phi 2 inverse t by dt is 1 plus t square of 2t minus t square minus 1 of 2t by 1 plus t square, which is 4t by 1 plus t square. So a of p times 1 minus t square 1 plus t square into 2 is equals to 2 equals minus y, and a of phi inverse of t times minus y is basically 1 minus t square by 1 plus t square, and also you could also do this where t of 4t by 1 plus t square is exactly x is 2t by 1 plus t square. Both should give you the same answer. Plus t square cancels off, 1 minus t square cancels off, and a of phi inverse of t is basically what the heck, 1 by 2. Phi inverse of t is equals to 1 by 2. Wow, wow, wow. Now that is interesting. So a phi inverse of t is equals to half. What we want is a of p. So how do we get hold of that? So a is a phi of t, phi composed with phi of p, right? So a phi inverse of, wow, I mean it's just constant. It doesn't matter. It doesn't matter. Because it's a bijection, right? Since it's a phenothism, R1 to, like locally U plus is basically R1. So it sucks. I mean, it sucks in the sense that it doesn't matter what you gave it. X by 1 minus y. I mean, it doesn't matter because it just doesn't depend on anything. It's just a constant. It's half. So a of p is half. Wow. What the hell, man? Yeah, basically this is 2x. This is 2y minus 2y. So a of p minus 2y is equals to minus y. A of p of 2x is 2x is x. So a of p is half. So what we have is, in fact, so the vector field x of x comma y is equals to minus y comma x is basically half of del by del t, del by del theta, or let's just say theta, right? This is precisely phi inverse of del by del t. Wow, makes sense because I think it makes sense because it's yeah, from our own intuition of physics, I think it makes sense. So this is interesting. Whew, interesting. Okay, consider x. So in the chart we want to write the local expression for x mu. So note that we have been using the fact that S1 is a regular submanifold of R2 and use the subspace definition of the tangent space at each point of s1 giving us a to write vector fields on it, vector fields as functions from R2 to R2. Now however, in order to VF local formula is true locally for all vector fields, all manifolds, and now need to rewrite x in this form. So we have 5 from u plus 5 plus t plus 5 plus u plus to r with phi of x comma y equals to x by 1 minus y comma phi inverse of t equals to 2t by 1 plus t square comma t square minus 1 by 1 plus t square. Then so of x comma y equals to minus y then x of x comma y is equals to minus y dv x and x what p what x comma y let p equals to x comma y then what p plus x frac partial y at word p equals to sum a of p frac theta, where a of p is a CTU plus and theta is the basis of TPU plus. That is nice, right? Makes sense. We want to find a of p. The above can be rewritten as I think it is very important to define this snippet. Snippet px partial x I basically frac partial x and snippet. Yep. In fact, px yeah, snippet py partial y line frac, let's go partial, let's go another partial y and then snippet. And one more very important thing is p dot or pp, maybe pp, right? I don't know. pp partial something frac partial snippet. This is going to be an important one. Okay, so we start with minus y px plus x py, wow, equals to, okay, important thing, we'll write f here, and then yeah, it's evaluated at p, so that is there. You want f here, and it's evaluated at p. This is equals to a of p pp theta, अच्छा f भूल जाता हूँ, f is also got at p. So now this becomes a of p phi inverse star of p theta and yeah, of f, yeah, so p, so f star inverse of phi of p, phi of p. I forgot to add the star now. Oh man. My t is actually just t. Okay, this is again, this is just a of p times, okay, I think, yeah, I think it's just total derivative, not the complete derivative. Just d, actually. Well. Yeah, dt just d, and yeah, now d by dt of f circ phi inverse of phi of p. Yep, which then is just a of p using chain rule. We just use the chain rule here. A of p d track d phi inverse of dt px, I think px partial of x, but f word p plus a of p track d phi inverse of t. I think I should not do that. dt of f y word p. I think that is this gives fp equals to half, and we have x nice. I can repeat the same calculation with does it feel like it's a constant vector field? It feels like it's correct, but on S2 things will be similar. I can do. Should I claim something? Should I claim something? Is equals to A of P del by del theta plus B of P del by del phi. Let's just say, right? Let's use the polar coordinates. U plus पोलर कोऑर्डिनेट्स को क्या है एग्जैक्टली? Yeah, we haven't analyzed the polar coordinates actually, right? But you can just write it as, I mean, I'm just writing it like that. I think they're both interesting questions one can ask from a physics point of view. This is basically this one minus this one. So 5 plus u plus to r2 will be x comma y comma z to, I'm just going to take the stereographic projection formula, right? Of course, x by 1 minus z comma y by 1 minus z, and the inverse, phi inverse of t comma s comma t is 2s by 1 plus s square plus t square to t by 1 plus s square plus t square minus 1 plus s square plus t square by 1 plus s square plus t square. Okay, that is this, and now we basically calculate. So what we do is, in particular, we just have EQL Q minus y px plus x py plus plus 0 z equals a of p. Wow, that is interesting. You know, del by del theta, del by del x, del by del y, del by del z is phi inverse of, this is phi plus inverse star of del by del t, phi plus inverse star of del by del s, or del by del s, del by del t. Then okay, and then you apply on s, so basically this will give you del by del s of f o phi inverse, and then you have phi 1 inverse del by del x, so del by oh shit man, del by del s, what the fuck, times del f by del x. So del phi 1 inverse del by del s plus del phi 1 inverse del by del t of del f by del x, but again a of p plus b of p. Well, s is basically s to r, it's gonna become z to r, so then I think it will be just 0, right? well. And okay, I'll just compute it sometime and just add it here. Okay, I mean, it's just a matter of minus. Okay, let's just try to evaluate one thing first. So phi 1, the derivative of this twice for the phi 1 component is 1 plus s square plus t square of 2 minus 2s of 2s by s square plus t square. Yep. So plus, so 2 of 1 s square 1 minus s square plus t square by 1 plus s square plus t square whole square. Oh yeah. This is the first derivative of p. P of minus 4st by plus t square whole square. This is equals to 1 minus y. Wait. Take that. Whole square. Fucking whole square. Fucking whole square. There's a fucking whole square. let's not compute this right here. In the interest of time, let's not do that. So let's go ahead. There's the first page and stop for a while. It was a good computation to do, practice to do. So okay, so what we now discuss is vector fields as derivations. And vector fields as derivations. If f is a C infinity function on M and x is a vector field on M, then define the function xf from M to R given by xf p equals to x of p acting on the germ of the function of p. Germ function p. So what you're seeing is you're defining another what? See, x of p is basically a vector field on M, and x is vector field on M, and x of p in particular, it lands in a tangent space, so it eats a vector, it eats a function M, function on M. So what you're saying here is that if you give me a function f on M to R, I can give you another function on M to R via, or sort of a canonical, so, I mean, x is itself not an M to R function, right? Yeah, it's just isomorphic to, it's just isomorphic to all the derivations. It can produce derivation by acting on function. It gives you xf gives you an, so in some sense it takes the infinity M and gives us the infinity M function, right? Yeah, in this sense they eat functions and give out functions in this sense. So yeah, we'll define xf into R. Yeah, so we claim that xf is a smooth function So how does this follow? What is x of p? It is written in the frames del by del xi, local frames del by del xi, linear combination of local frames. Acting on fp, you get basically the derivations of these f. Since f is smooth and phi inverse is also smooth, then this locally this is smooth. That is pretty trivial. So yeah, if u comma f xn is a chart of M, then x of p equals to summation ai related p xi, which is also validated at P, for some ai in C infinity U. Right, this is a local frame expression for the vector field. Yeah, it's interesting that tangent bundles have these local frames ready for you. Basically the basis of tangent space, right? Yeah, for any sections you don't know what the structure of each vector space, but yeah, when you attach a tangent space, you already have a canonical basis on these tangent spaces through the chart diffeomorphism to Euclidean space. So after you write this expression for x, we can write, so x of p acting on f, the germ of the function of p, is basically p dv f f f and xi divided p. Now what this is basically some ai of p pdv f circ phi inverse xi phi of p, just what we did last time. Since f and f is smooth and phi is the diffeomorphism and phi is a diffeomorphism, we have x acting on the function f, xf, locally in the chart U is smooth. Cool. So a quick example. Let we are considering vector field on Rn where x equals to a 1 1 plus plus and So okay, what you want to show is that xf is another function. Xf is basically then x f of p is equals to summation I of p p. So, sure. I think we did show that, right? I mean, sure. The way we acted here, the effect on f, right? On f, this is clearly smooth. Yeah. We can also consider the curl-like vector field. This one. See that. This is clear from hence any vector field x in M gives a map x from C infinity M to C infinity M, right? And in fact x is a linear map because let D be the set of linear maps. D to satisfy in the map very. Then the proposition is that if X is a vector field on M, X is smooth if and only if for all f in C infinity M, xf is smooth. That is interesting. X is smooth if and only if xf is smooth. I mean, Okay, we then move forward to vector fields push forwards. And, yeah. Okay, this lecture is taking a long time, mostly because of the calculation that we had to do. But it's nice that we were able to do. It's already 2 hours. Oh, I see. It's okay. We had to do that. So we'll define vector field push forwards now. But before that, I'm going to take a break.